Wall Street Journal happened to kind of claim the beginning of a post-transformer era.
Łukasz Kaiser triggered a revolution in artificial intelligence.
Adrian Kosowski,
the inventor of Dragon Hatchling,
to tell us about transformer replacing architecture.
This is Mathias, pioneer of liquid networks,
CTO and co-founder of Liquid AI.
Llion Jones, one of Transformers' authors, founder of Sakana AI.
Ladies and gentlemen, welcome to the main event of the evening. 7 rounds of questions and discussions with the biggest and bravest minds in AI. This is the heavyweight battle of ideas. My name is Zuzanna Stamirovska, CEO of Pathway and co-author of the PDH architecture.
And my name is Dexter Horthy, co-founder of HumanLayer.
We are gathered here tonight to discuss the deepest layers which sparked the AI revolution. Transformers versus post-transformers. The math that shapes trillion-dollar markets. And who knows, the future of humanity. All right, now without further ado, let's welcome our contenders. In the purple corner, we'll have 3 challengers to the belt of the ruling architecture, advocating for dynamical systems, latent reasoning, continual learning, and whatever comes next after attention as we know it.
And the first challenger to the title, the evolutionary architect, co-author of the original Transformer paper, now stepping into the post-transformer corner. The rare challenger who helped build the belt he is now trying to take away. All the way from Japan, CTO of and co-founder of Sakana AI, Llion Jones! And the next challenger to the title, also in the purple post-transformer corner, the dynamical systems guru, the MIT AI researcher, co-inventor of liquid neural networks, the CTO of Liquid AI, Mathias Lechner!
Okay, now the next challenger to the title of the ruling architecture. The reasoning disruptor, quantum physicist and theoretical computer scientist, the inventor of the Dragon Hatchling BDH architecture, CSO of Pathway, Adrian Kosowski! Woo! In the blue corner, the reigning attention champion of modern AI, the logician, co-inventor of Transformers, the architecture that changed everything, creator of ChatGPT 01, 03, Lukasz Kaiser!
Tonight, we are here to establish who wins, the Transformers or the post-Transformers. Who will bring the next era of AI? Okay, so we got some rules. We will start with each contender presenting their case, either Transformers or post-Transformers, in 5 minutes.
Correct. And then we'll move to rebuttals, where each will have 3 minutes to respond to the points made by their opponents. Important, in the rebuttal stage, each of you can raise your gloves to signal a point of information or a challenge, and then the active speaker may accept it at their leisure.
Then we will move to short punches in 3 rounds of 4 minutes each. One contender will be asked a question by Susanna and me, and the others can jump in freely. It's going to get chaotic. Then we'll do some short closing statements, and we'll open the floor to questions from all of you. And finally, we will make some noise to decide
who leaves tonight as the reigning champion of AI.
Contenders, please join Susanna at the center of the ring.
Come on. All right. All right, boys. Please put your kind of gloves up. Good, good, good. Okay. All right, now, for the AI champion title, give me a good, clean fight. Obey the rules, ground your statements in evidence. Now, touch your gloves and have fun.
All right.
Oh. All right. Round number 1. Łukasz, we're starting with the opening statements. You can go to the center of the ring, or wherever you want to be. Yeah.
Thank you very much. Thank you for the invitation and this amazing match. So I'm here to talk about transformers, which is a little weird because people who invent things, they have this tendency to actually oppose them more than others. I worked with Jeff Hinton for a while, and he hated backprop at that time. He was like, you need to find something better. This can't be. The brain doesn't work like this. This backpropagation thing that just can't be the solution. And I felt for many years the same about transformers. But Jeff Hinton has given up on backpropagation, and maybe, just maybe, it's time to come to terms with Transformer 2. It is an amazing surprise to me, and I think to Llion as well, and many other people, that this insanely simple machine that predicts the next token in a sentence or a longer text is able, to chat with you and now write your code and click your windows on your machine and soon do a lot of our work. But it works. It works, and that's the very key thing about transformers. And that is something that many other systems don't quite do. I just recently tried RNNs again, and they still don't really work. So that's the first very important argument. The other argument, though, is like I came from the RNN times, so I love recurrent networks. So I want to think about transformers not as an attention network, but as a kind of memory. So if you think of transformer as a memory, how does it work? Well, imagine you're a librarian from before the internet times, and books come to you, and you need to, you put them on the shelf, and you need to somehow find them, right? People will come and say, what's the book with this person, or what's the book with that? How would you do this? And if you've ever visited a library that still had these systems, you have these paper cards where you say, this and that, it's this book, it's there, and it's maybe on this page. So you write a key, which you will search on your cards, and then you write a value which tells you where to find this and what it was. So the transformer is exactly an RNN that whenever a new information comes, writes a key, puts it into its key store, and then writes the value that it needs to retrieve and puts it there. And when a question comes, it finds the key that's most similar to this and gives you the value, except it needs to be differentiable, so it's soft. And that's it. It's an extremely simple and fundamental form of memory that just concatenates everything that comes, it just gets longer. So it's a very fundamental thing, and it just has to work, right? It just remembers everything. Now people say maybe it should forget some things, and these days, the context gets too long, it forgets something, it compacts it. You can add this on top. And it's the same with reasoning, right? You cannot always do the reasoning in your layers. You need to maybe have a chain of thought. Okay, you add this on. You don't have enough parameters, you add an MOE on. But it's simple and beautiful, and it works. So there it is. That's the case for the transformer.
Thank you. All right. Now over to Adrian. Bell ring.
Thank you. So I'll be making the case for the post-transformers, but most of all, I'll be making a case for intelligence. Intelligence is a big topic. Now, we've all talked about like artificial general intelligence, super intelligence, and so on. What's intelligence about? It's about the ability to solve difficult problems, to deal with difficult problems, especially problems you haven't seen before. And up to recently, as humans, we considered ourselves to be the only intelligent species on Earth. Today, every day, if you consider what's happening, millions and millions of very difficult problems, problems that can be considered close to the pinnacle of human ability, are being solved by two intelligent species, humans and transformers. So, what am I saying here in the post-transformer camp? This is the post-transformer moment. It is not so much about saying the transformer is bad. It is not about saying that the transformer is a bad example of intelligence. It is about saying that we have several examples of intelligence, and what are we to do next? Build more? Well, that's not the point. The point is that now we can discover the common theme behind intelligence. And every kind of intelligence has its shortcomings. Łukasz mentions the advantages of the transformer. As a form of intelligence, the transformer has shortcomings like problems with continual learning, problems with long-term memory, lack of reasoning in latent space unless it's hacked in a very complex way. Right? So these are all problems with the transformer. And what comes next? What will the future bring? Will we be just having more examples of systems that patch up here and there? I think the answer is different. Łukasz, you mentioned indexing in the library as the example of a thought model for the transformer. I will anchor on this. Back in the 90s, there was a problem which is just a tiny subset of intelligence, which is indexing information. That was the big challenge of the 90s. The web was young. Web search engines like Alta Vista and so on were around. We had examples of that. And then there was a company that came with one big theme, one mathematical equation, and one way to implement it. The equation is called PageRank, after one of the founders. The way to implement it is called MapReduce, and the company is the largest software company in the world. I don't have to name it. And one way to get that theme of information indexing changed the world as we see it. I think we have not yet had a PageRank moment for intelligence. The theme behind intelligent systems is not fully discovered. The transformer is a form of intelligence, but if we discover this theme, we understand what this theme is about, we will get further. And here we can talk about better reasoning, better memory. As the creators of the BDH architecture, we can give you an inkling of the answer. The answer that we are giving is that this theme is all about the ability to do latent reasoning in high-dimensional spaces, combining the advantages of state space models with sequence processing. So absolutely not saying that the transformer is doing things wrong, just saying that there's a fuller and a more direct way to implement this theme. For this, I'm making the case for post-transformers as the search for the theme of intelligence, the leitmotif that will bring us even further than we are today. That's my case. Or is that the wrong thing?
Who's next?
Now we're having Mathias Lechner, please.
Thank you so much. I want to share, to answer the question, how we at Liquid AI build foundation models. And for us, it's not a question of transformers or post-transformers. It's transformers and post-transformers. So the thing is that we design models not in a vacuum, but with hardware in mind, with use cases in mind, with capabilities in mind. And so I, as a researcher, as a scientist, and as an engineer, like to draw from as many building blocks as possible. To give you an example, we have a language model with GPT-3 level capabilities running on a Raspberry Pi with about 40 tokens per second, so really fast. And how did we achieve this? Not with a transformer and also not with a post-transformer, but we just took whatever works for the requirements and for the capabilities and for the speed that is available to us today. And so whenever there's a new attention mechanism that's being introduced by DeepSeek, multi-latent attention, compressed attention, and so on, I'm happy. And every time there's a new post-transformer model that's being released, let it be SSMs, a new Mamba, a gated linear attention, convolutions, or whatever is there, I'm also happy because it allows me to draw from a wider set of architectures. And the reason we do this is because we don't live in a static world. We live in a dynamic world, as I mentioned before, where the requirements and also our expectations on AI changes. At the same time, also the research is not static, that we just, we stop doing research today and then we have to decide. No, it's dynamic. We are working with agents that are discovering new layers, new variants of models. So again, and this will accelerate in the future with more and more AGI as we come closer to it. As well as we are not living in a static world in terms of hardware. So as I mentioned before, deploying on a Raspberry Pi is very different than if you have access to the next Vera Rubin NVIDIA stack and so on. That's like, like a megawatt or so of power that it draws. So all in this context need to be considered. And so for me at least, or for us at Liquid, really means that we want to draw from all possibilities to build the best model that we can do today.
Thank you. And now the last contender, the one who switched corners.
Thank you. I feel like I need to start by admitting that I'm a little bit nervous, partly because this is the first time I've done a debate-like thing, and this setup is extremely bizarre. The second reason that I'm nervous is I've learned over the years that quite a good way of knowing if you're wrong is if Lukasz Kaiser disagrees with you. So it might seem unfair that it's 3-1, but I fear not. Nevertheless, I will try my best. So, opening statements. The first concession I will make is if I was in Lukasz's position, I think maybe I would be on his side. Because if you think about the motion, right, transformers versus post-transformers, I should say briefly what I actually take that to mean. It's, are we done? Right? Is transformers really the last word? Do we just need to just keep incrementally making it better and scaling, and then that will get us to the goal of artificial superintelligence? Now, a company like OpenAI, it makes sense economically that they concentrate on transformers, right? They're arguably the best in the world right now. They need to keep that lead. So it makes sense that they don't put any money in looking for what's coming next, but work on what's working right now and keeping that moat. But for startups on the other side, I think it makes more sense to put some money behind the long bets, actually taking time to find what's coming next. And of course, don't forget, OpenAI was in that position at some point, right? They were the ones that were looking for what was coming next, and they found it, right? They found that transformers scaled better before other people, and they've done very well of it. So it would be almost hypocritical to say that we shouldn't try to do the same. Secondly, I think it comes down to goals. Now, I'm going to be honest, I am sympathetic to the idea that if we keep scaling transformers, we might actually get there, right? We might actually get to the point where we will be able to call something artificial superintelligence. It's just that I have a very strong intuition that there's better. Right, so I've come to see transformers as obviously a very elegant architecture, but I think it's actually brute force. Right, the amount of data and compute that we need to actually get these things working is immense. A human doesn't need to read literally everything on the internet several times to become almost as intelligent as a human. Okay, so there's something better out there. And I think it's not just an intuition. We all have a proof of concept here, our brains. Our brains can do things that transformers can't. And I think that's screaming that there's a gap that we still have to fill. And people are putting a lot of effort into filling this gap. But they always seem a bit hacky to me. So someone on Lucas's side might say the success with reasoning that we've had recently, and now we can have these things that code amazingly. Yeah, amazing. But isn't it a hack? Transformers don't reason natively. We have to manually put a good old-fashioned AI Python program around these things in order to feed the output back in correctly. Right? If the transformer was really as powerful as we think it is, shouldn't it be able to learn to reason natively? So that's one of the things that I would like to see from the next generation. And I'll finish on this point. I actually think that the success of the transformer is stopping us from finding the next thing. Right? That people are concentrating way too much on this architecture, and that it's so successful and so good at what it does that we're really stuck in a local minima right now. And it's going to take someone to do something very different to find the next thing. And my final point is, anyone on Lucas's side, I think will absolutely, when we find the next thing, will be forced to move to our side because they just won't have a choice. Thank you.
Wow. Impressive. Amazing. So now we're going to move on to the rebuttals, which is the part I'm most looking forward to. Each of our contestants, we're going to go through the same order, and each of you are going to have 3 minutes to give your response to everybody else's opening statement, everybody else's rebuttal. And this is a special stage because other contestants can sort of signal we'll call it a point of information or perhaps a contention. So raise your glove if you want to jump in. It is up to the rebutting speaker to decide whether they want to call on that person or keep going. We only have 3 minutes, so we're gonna go fast. Oh my God, what's the next one? Amazing, no more lines. Let's give it back to Lukasz, and let's hear what you think of these, dare I call them arguments.
Thank you very much. I think they're quite amazing arguments. I'm very sympathetic to them, but I do want to put them. That's why I started with Jeff Hinton and backpropagation. There are so many better ways to put information back than to backpropagate. And you could say it's very brute force, but then, people have found implemented losses that go through layers, and they can be implemented on smaller hardware. And I have heard this argument that we're going to use small language models on little hardware for so many years, and I click the best model on the highest thinking budget every single time I use any AI. And I think so do many people. So while I think all of this is true to some extent, I do believe that for the next thing in AI, you need to go for what's most intelligent. And the recurrent architectures of sort as a contender, I think they're very beautiful, but you can see transformer as a recurrent architecture with a very simple memory. That's one thing. So you need to do something better than that. And I very much concur with Llion that it does feel like the human brain does something better. And one way in which we may be very, so I actually did implement transformer as an RNN and a bunch of old RNNs last week just to compare. So a very small GRU, I don't know if you remember GRUs, they were like a very simple kind of RNN, runs about 50x slower on current NVIDIA than a much bigger transformer. That's damning, because if there was a beautiful RNN, you'd need to use like 100 more compute currently, like 100 more wall time, not compute. It's actually less compute if you count the flops, but it just because it's sequential, it's run so slowly. Now, hadn't it been for the transformers, maybe we would have had hardware that does loops faster. It's not, it's a choice, right? It's not inherent. There is a little bit of inherent though, like it's much easier to make parallel hardware than hardware that's very sequential, but the sequences are not that long. So I do concur with the fact that we have, well, we definitely are nowhere near either explaining the human brain or matching like the data efficiency and beautiful of human generalization. So there is something to be done. But on the other hand, if we look at machine learning and not psychology, it does not feel like we have the methods there, and the hardware doesn't seem to be there. So how can we get there? Well, that's the challenge, luckily not to me, but to my post-transformer opponents. But maybe, just maybe, it will be the transformer that finds it, and not you.
Oh, Łukasz, you landed so many punches. I was going to challenge at some point, but since I'm speaking next, I will kind of punch back 2 or 3 times on that. But just the turning punches. Actually, a lot of the things that you mentioned in one flow, like recurrence and backpropagation, they are kind of connected in a way. Personally, I think there's nothing much wrong with backpropagation through a number of layers, right? The reasons why some hardware like our brains maybe does less backpropagation is just that it doesn't know how to, or because it's difficult. But if you have the ability to backpropagate, why not? And backpropagation is actually amazingly good in during learning. But there's a difference between reasoning and learning. When you're reasoning, you are like at the very least running an algorithm which is pretty deep. You go through many steps, and whether these steps unroll through chain of thought, or whether you do them through recurrent latent state, they unroll over a long period of time, and you want that during reasoning. On the other hand, in learning, if you try to propagate the gradient backwards through all those steps, that's a mess. Bad things happen to gradients when they're backtracking the long paths. So there's a good reason why the transformer, which has its compromise, let's call it that way, between depth and recursion which is very closely tied to chain of thought and so on, why it is trainable. We believe that this compromise can be shifted a little bit to take away one of the bigger limitations, which is the necessity to produce long chains of thought and the inability to think in thoughts, right? Because transformers think in language. They do not think in latent thought. They memorize their thoughts, but they think in language. So this is a challenge, and the solution to this challenge exists and is beautiful. This is what I wanted to say. We are up for this challenge, so thanks, Łukasz, for giving this challenge up. We are taking it on. What else is there to say? Any other guy? I have time to punch, so guys, if you have my 45 seconds now, then I'm handing over. Yeah.
About hardware?
About hardware, yeah, about hardware. So about hardware. The architectures that we have are fitted into hardware naturally. The fact that RNNs fit badly into matrix multiplications is a problem with RNNs, which we are not contending, and we are not called the RNN club, we are called the post-transformer club. There exist better things. There are better things which deliver on matrix multiplications, which take full use of gems and so on. So definitely you can propagate state. Another thing that I should say, having 6 seconds left, is that RNNs have too little state and the brain has a lot of state, and that's why the brain works and RNNs don't. Thank you.
All right. Quite the counter punch back. Thank you, Adrian. Let's give it up to Mathias.
Thank you. Yeah, I want to mention 2 points. First one, again, like that there is a blurry border between transformers and RNNs, as mentioned by Lukasz. So imagine you have a transformer with a very efficient KV cache, like latent and like very small per step, versus an RNN that has a massive state, like think of gigabytes or long or more than that. So I think it's at that point where like the line between a transformer and the RNN becomes very blurry. And so this is one thing where it becomes philosophical.
Which one would you take?
Yes, exactly. So this is one thing.
Transformer.
No. Maybe. And the second point is
Jeff into fast weights, would that be a good term?
fast weights, yeah, or even like something else, yeah, fast weights actually as a memory storage. That's a good point. Which is again a kind of an RNN if it operates over a fixed budget. But even more important, as it was mentioned a couple of times, that the brain doesn't grow, like when you grow older, right? So it's like a fixed state in that sense, at least in terms of atoms that it is in there. So it's kind of that, you know, asymptotically, like if you want to build like HEI, we already have a realization of intelligence with a fixed state. Again, can be massive actually, which brings me to the first question. But given the insane progress that we have with the transformer, and why the transformer is so great is because now we have all of these agents, all of these things that are working autonomously, and I believe that they will find their own replacement. So I think it's like not maybe us that will find a better architecture. I hope so, but in the worst case, I'm convinced that the transformer will find its own replacement.
All right, I get it. Yet another crushing blow from Team Post Transformers. Rounding it out for us, let's hear from Llion.
Yeah, I think the fact that we started talking about RNNs is indicative of what I was saying before and how stuck we are in the current paradigm. The transformer breakthrough, I think, is deeply misunderstood. Okay, people look at that paper and they think, wow, they moved around, you know, the same standard components of a neural network, multi-layer perceptrons, attention, residuals, pointwise activations, and they happened upon this architecture that works really well. So people, right, other researchers, seem to think that, oh, if I keep shuffling around these components, I will discover the next thing. No, you won't. Stop it. The breakthrough, as Lukasz alluded to, was hardware. It was the fact that we were able to process tokens literally thousands of times faster and scale better. That optimization is no longer on the table. And actually, if we had the computational power to train RNNs, we're pretty sure they would be as powerful as transformers, right? Pound for pound, parameter per parameter. I can see Lukasz disagreeing with me there. So we need to go further, okay? We really need to start questioning all the assumptions that we're making about neural networks and what they should look like and how they're trained. Right, for example, the most speculative stuff we're looking at my company, we're not even sure can be trained by backpropagation even in principle, okay? You really should look at even hidden assumptions and try to do something completely different in order to get out of this local minima. The other point I wanted to make is I think there's sort of a weird cognitive dissonance we have as researchers and as a community. Simultaneously, we know a breakthrough is coming, right? They eventually come along, but at the same time you feel like they're not and you're always surprised. So I think what's going to happen is, you know, Lukasz is going to be correct up until that day, and then he's going to be wrong forever. And it could happen at any moment, right? You know, somebody might have worked something out on some computer somewhere and we just haven't heard about it yet. But you really, really do have to go much further out of what the current architectures look like in order to find the next thing, in my opinion. Thank you.
Wow.
Okay.
Okay, what's next?
Well, next are the quick punches. So we'll have right now 3 rounds, 4 minutes each, and we'll be asking you questions on specific topics, and you can discuss however you like, almost as if you were, you know, at lunch, just that you're in a boxing ring right now. So
don't actually punch each other.
yeah, I mean, no world-class researcher suffered during production. Okay, so quick exchange. Round number 1. The nature of intelligence. Who wants to start? Łukasz, maybe. Since you kind of know.
What is intelligence?
Sure. So, you know, I was very interested in AI when I was like 14 already. And this question comes up and up, right? And at some point, people started saying, intelligence is just your ability to do things in the world and get the outcomes you want. And so this is basically the definition of RL. I don't think this is a great definition of intelligence. I think that I think you should go deeper. As a researcher, I am not satisfied with this. But the reason we don't have a much better definition of intelligence, and the same reason, you know, there is this Turing test thing that we don't talk very much about because, you know, it has sometimes floated away with this chat thingy, is that whenever you start to try to define intelligence, we all have this feeling. I have the feeling that Llion has very much, that there is something very deep we don't know as a researcher. And then I wear my engineer hat, and I'm like, you know, you need to define intelligence as what you observe the system does, not as what it is, right? Like in the Searle's room, the intelligence is not in your biological substrate. You need to have something that you see that is intelligence. And once you come to that, you're like, okay, what can I see on the current hardware that is intelligence? And that's the transformer.
So I will pick up, Łukasz, on what you said, if I can. The intelligence, first of all, this is a point to the audience. Intelligence is not a thing. It's not a product. Intelligence is a process. Intelligent is part of information processing. Intelligence is a way of doing things. So I hope you all know the difference between a product and a process, like a Toyota car and a Toyota process, right? Intelligence is a process. It is the process of solving things. No. So intelligence is a way of doing things. Intelligence is a way of doing things can be viewed algorithmically, right? That there's an algorithm that is running, that's somewhere in our minds, there's a certain process, a computational process that's going on that delivers. It can be seen with a dynamical system lens, that there's an evolving dynamical system which delivers. This is not a coincidence that I mentioned PageRank when opening. PageRank is a process. It is a very, very, very small chunk of intelligence to index information, right? To be able to build up in your head an index of knowledge. PageRank is a process, and intelligence is a few processes like that which allow us not just to index information, but to process it effectively. So I think the process can be discovered and is still waiting to be discovered because the transformer did not discover the process.
Do we think that the kind of the obsession with the transformer, maybe as Llion said, is basically, are we just confusing current engineering convenience with like what might be described as long-term scientific truth? Is that accurate, or is that way oversimplifying?
The transformer is an embodiment of intelligence. Humans are an embodiment of intelligence, but what the process is that is intelligence is not quantified. Now, if I were to ask you today, Łukasz, where you see PageRank in a transformer, would you be able to take that? Because you said that you see a library in it. Do you see PageRank happening?
No, I don't see PageRank very much. But I'm very sympathetic to your argument, which I do think gets at the core of it. But let's...
So one thing that the current paradigm has correct, I think, is we've actually landed on a very weird definition of intelligence. It's how good are you at predicting the next word on the internet? And I think, in my opinion, intelligence is compression. So you compress the internet better, you're more intelligent. And I think, you know, the next thing, we still need to apply that metric.
That's all right. I mean, do we want to keep on going with this round? The nature of intelligence? You make some noise if yes. Big noise! Noise! Yeah. Okay, we keep on going. Matthias.
Yeah, I think intelligence is difficult to quantify. So I think there's a cultural component of like maybe different cultures have a different opinion on what counts as intelligent. But yeah, there's a lot of different things going on compression, on predicting, and so on. So that's why, like, I think it's just there's no clear one definition. Maybe my one is just how humans differ from like other material or like animals as a way, but it's also like subjective, I think.
So I have a question. I mean, transformers fundamentally deal with language. Is that correct? I mean, in a way. I mean, they were developed as language model for thinking. Okay.
They deal with sequences.
Fair enough.
But these sequences can be proteins or images or sound.
The original name actually comes from the fact that we wanted to transform any data into any other data.
Right. So now when you think about reasoning, right, where does language fall into reasoning, and what's the link between kind of reasoning and whatever like we're doing in language models right now in terms of what intelligence is?
Yeah, I think language embodies intelligence, right? So this is why these things are so successful. But I think it's a good example of where these things fall short. We force them to think in language. And there's definitely some mental processes that we have that are not grounded in language. So that's something that we need to have in a post-transformer.
What was it that Wittgenstein said? If a lion could speak, we would not understand him.
Do you understand me?
Are you a lion? Oh, wow. Damn. You beat me in my own joke. Please.
I do want to counter, as we just said, they are sequence models, not language models. These sequences can represent other things. It's just they represent words now because that's our pre-training. But that is not a transformer's fault. And when transformers do visual reasoning in the newest models because they operate on images. So I do not believe it's their limitation that they operate on words.
How would you say, how do you rectify said that perhaps the part of reasoning that's related to discovery, to the discovery of things that were never said, is harder to express in language? It's possible, but it's much more verbose because it hasn't been said before. It's like the moment of like writing a scientific paper, right? The moment before you've actually written it up.
Well, as you know, I have a lot of sympathy to this stance, but you do need to take into account that there was an Erdős problem that was open for 60 years and no human solved it, and it was solved by GPT 5.5 a week ago or so, right? So, and it was never said. It was solved in words. Probably you can solve it faster in non-words. But then, because people want to say vectors, but then they go to 8-bit precision. And vectors in 8-bit precisions are words. They're just words in a different system, but the transformer really doesn't care that much. So can you shorten your chains of thought? I'm sure you can. I don't personally think this is that crucial. I think way more crucial is, in addition to transformers, I also have kids. And because everyone tells me long reasoning is great, and I look at my 6-year-olds and they get to amazing places and they don't spend 2 hours on their chains of thought. If there's anything they do not do is to reason for very long. So they manage to achieve somewhat impressive feats extremely fast. And because I also want to say, the transformer is so parallel for the parallel hardware, but it seems like the brain, if anything, is even more parallel and even faster. So maybe, though, it is then just even better transformer.
Any other questions together? No, so we're moving to the next round. All right.
Time for round 2, scalability, and everybody's favorite topic, scaling laws. Adrian, is scale still the master key? Is being able to scale still the most important part of this conversation? Oh, Llion, let's go.
Unfortunately, yes. There's something called the bitter lesson, right? And it makes AI researchers angry because if you want your system to do better, you have 2 choices. Either you can do interesting things like changing the architecture, changing the hyperparameter, changing the data, the way you're training, or you use 10 times more compute and 10 times more data and you win, right? So it really is the scalability of the transformer that made it successful. And any post-transformer will have to demonstrate the same thing.
Mathias, you got ideas for us?
Yeah, I can just agree like that. Yeah, we train small models and like basically 2 orders of magnitude of different scales of models, and like there's clear scaling laws in like all different architectures. So I think it's just naturally like that you need to spend compute and also storage specifically. Like you wanna like to store the entire thing of the world, the entire internet. It takes some memory. And I think that's why we see still like strong scaling laws and also like compute as a way. But I agree to the point before, the reason that most models reasoning text space is just there's data available, but it's not the most efficient way to think.
Yeah, and I mean, we know that different models have different scaling laws, right? And I think there are actually some models that appear to have better scaling laws, but not as adapted to the hardware. So I see no reason to imagine that actually there's something out there that has drastically better scaling laws. And if we find it, we will have no choice but to move over to it.
I am very much in the scaling camp. Transformer has, if anything, started this camp. There was a talk about RNNs. I think scaling is not just put more compute. I think some models scale worse than others. And I think that is a real problem with the model, if anything. If there are models that scale better, bring them on. Luckily these days, with all these data center build-outs, you can afford 20x more compute. You can afford 50x more compute. If you've done the low of the scaling curve, like you can't afford it to maybe launch it, but on the research side, you should be able to show, if you show me this curve, that it goes down steeper than transformer, I may need to concede, but I have not seen that curve yet in a convincing way, at least.
Yeah, this property also worries me that, you know, if they're so good at scaling, and we have hyperscalers now, you know, like I say, humans don't need to read the entire internet. But I kind of feel that the answer given by the transformer side is, well, we can train on the entire internet. So what's the problem? But I think if we found something more efficient, then that would be preferable.
I want to warn though, because there may be something that is more data efficient, but does not scale. And that would be a really scary architecture, because this would mean that we can make great progress on learning from less data, but it will not actually beat the transformer when scaled up. That would be a little sad. I actually personally don't think that is the case, but it is not an impossibility.
There's just one element I wanted to add, because it's hard to disagree with anything that's said, but one of the things that the transformer said when setting the scene, and I think we should revisit, is that all the types of scaling go together. So scaling in data, scaling in size, scaling in compute. Other architectures may scale differently by uncoupling these different elements. And in particular, if we look at kids scale differently. With very little training data, they can be forced to do a lot of compute, and you can have, like, chess grandmasters at age 5 or whatever. So there's a way to have architectures which don't couple the different types of scaling. And there are still some, just to return a punch, there are still some niches out there where training data is limited. There are some areas of science, there are some areas in enterprise even where data is limited and there cannot be more. So the challenge is really how to deal with those limitations and scale up compute without scaling up anything else.
All right. So now we're moving to round number 3, real-world deployments. We can start with Mathias.
Yes, yeah, and I can just connect to a point mentioned before on real-world deployments, because text data is like all like hype at the moment, but like a lot of like important problems deal with different types of data. Protein, genetic sequences and other types of biomedical signals and so on. And some of them, not all obviously, it depends on each modality, but some of them we really see strong like scaling laws of performance from other architectures, like recurrent neural networks and so on. They just work better. We tried with transformers, spend a lot of compute, but just there's something inherent in the way these sequences are shaped that just makes a very strong case for RNNs. At the same time, also for real-world deployments, as I mentioned before, like speed and like the hardware matters a lot. So I think this is really like the architecture, at least that we see in the next couple of months or like years and so on, is really like co-evolving with the hardware. That's just unfortunate in both positive as well as negative directions.
Okay. If now I have a question about benchmarks, because this is something that actually people can try to show real impact of AI, right? And they run a benchmark. And is this how we should be, looking at progress and evaluating if we're really doing better with AI? Do they mislead us? I mean, are there the absolute truth? What's your take? Maybe Llion, since we mentioned that before.
It seems to be the best method we have at the moment, so that seems to be what drives forward progress, but they're far from ideal. Too easy to game, right? There's too much incentive in the industry to tune these models to pass these benchmarks, and that's not to say that they're cheating, but it's to say that, just doing well on these benchmarks doesn't necessarily translate to being good elsewhere, and I think we see that in coding models. So very important, but we kind of need better, but I don't have any suggestions.
Yeah, for the room, like what are the properties of better benchmarks? Obviously, if we knew how they worked, someone would be building them already.
I will say something here. When the transformer paper was done, there was a standard metric in translation which was called the blue score, and it was a little tricky to measure it. They had old scripts and stuff. And I think it was Noam who told me to drop this and just look at perplexity, the probability of the next word. It is an amazing metric that turned out to be much better, and then it correlated when it needed. And then the blue scores became irrelevant and perplexity still worked when they became too good. I think it's the same. The way OpenAI really benchmarks its models is perplexity on the internal code base, and I think a lot of labs do this. And it's the driving benchmark for most models. Of course, you need a data set that's nowhere on the internet and nowhere. So it's like the moment you release it, you lose, right? It has the same problem. But if you have a varied enough, good enough holdout set of text, maybe you need images, proteins, or whatever, just look at perplexity on it. It's really very hard to beat it. It goes at this idea of compression, and it's hard to imagine a benchmark that's dramatically better than that. I mean, there is a little asterisk to it that I could add, which comes when it's like reasoning, and like sometimes you improve your probability on very low frequency token, but whatever. There are little asterisks to it, but they're really small. It's probably better than most of the benchmarks, I would say.
Yeah, I'd just like to agree. I would like to see people going back to trying to push perplexity.
What a bunch of heavy hitters. What an incredible conversation. Where else in the world can you see this play out live on stage?
Insane. Yeah. Ladies and gentlemen, we just witnessed history happening in a boxing ring. When was the last time you were together?
Don't say last week.
In Japan.
All right. Cool. Yeah. So now it's time for the final points. Just kind of state your case. Each of you will have 2 minutes. I mean, you can, if you take shorter, that's fine. So, last words for each of you. And
starting with Lukasz?
Yeah, starting with Łukasz.
All right, let's hear it. Lay it down.
Well, I think I conceded at least in some way. So first of all, we should start a little company that has a held out set of text and code, and we'll measure perplexity on that set for a little fee for every lab in the world, and that will be the ultimate benchmark. I honestly don't know why no one has done this yet, but maybe someone really should, because it would probably be very good. And the other thing is though, like then you have this holdout set that you're not showing to people. Okay, you need to access to an API. You optimize for this. Maybe you take your best agent, but not for the best architecture because you can just train on more stuff, but for the best scaling curve at the best slope. Maybe that is the way to optimize machine learning model. I want to see something better than transformer. I would claim for now the transformer still wins, but I think at least we can agree on if we can agree on a metric that is some progress, even if there are asterisks to the metric, but if they're small, it's good.
You? All right.
All right, who's up next? Adrian?
So it's good to agree on a metric, and I think the challenge is on, definitely. I think there's one thing that has been said implicitly, but maybe should be said explicitly about the transformer. It is an architecture which is optimized for hardware for pre-train. Right? This is the original motivation behind having efficient transformers, that training is efficient. I think, as we move into a world where more and more time is being spent on inference and more time is being spent on reasoning, it is a perfectly honest question whether it is also the ultimate architecture in terms of use of hardware while reasoning. And here, you can see how well it's using hardware, how long the reasoning traces are, how far it can get with different use cases. So I think for this one, the jury is out, and I will remain in the camp saying that it is not the ultimate answer. It is an ultimate answer in terms of what it can do, because you can express anything using chain of thought at any reasoning. You can get to any reasoning, but it's not necessarily the best use of hardware to reason the way transformers do. So if I can bet on anything as being the next big breakthrough, is actually more efficient, more compact reasoning with less use of hardware.
Okay, more efficient, more compact. That's what's next. Mathias, what you got?
Yeah, I just can repeat to myself from what I mentioned before. Is, we bet on both. We bet on improvements on a transformer simply because it works and the hardware, as we discussed, as well as we bet and do a lot of research in post-transformers because it's, again, like fast and all of the reasons of why it's the brain and so on that we've heard. So for us, it's really like to hedge our bets in a way and to really explore whatever is possible.
Nice.
Yeah.
So I feel that Lucas's main argument was, well, the transformer is the best. But my point, of course, is for now. I was not given any reason today to doubt my belief that there's better. There are too many things that the transformer does not do well, and there's too many things that the human brain is capable of that the current state of the art is not. So I want to reiterate the point about breakthroughs. How, on the one hand, they come along every so often. They come along. You're surprised, but they come along. And I think it would be absurd to think we're in a world where there will never be a breakthrough in AI ever again. And when that happens, we will solidly be in a post-transformer world. Thank you.
Incredible. Great close out. So we're going to open up to the floor to some questions from the audience. Claire has the microphone. Raise your hand if you got a question. Is Claire doing the microphone? Someone's doing the microphone.
One over there.
Hey folks, that was amazing, thank you. I'm curious about two things. One, the hardware is just such an enormous part of this conversation. There's sort of a, I don't want to use the word like mafia sort of a feel to, there being sort of like one way to do it, hardware-wise. One sort of bottleneck that you can come up with all of these beautiful ideas, and they're so wonderful when you're, in a theoretical space, but when it comes time to ship, you sort of know that there's kind of one particular tunnel that you have to pass through. So I wonder, how can we move beyond the transformer if we're still stuck with the hardware that enabled the transformers sort of big moment?
Yeah, that's a really important point. What you're basically describing is the hardware lottery. And the transformer was literally us saying, wow, we have these TPUs now, they can do massive matrix multiplications. How can we take full advantage? And that fact makes us even more stuck in the local minimum. So I think what people need to understand is the first iteration of the post-transformer is obviously not going to be as good as a transformer. And people need to be comfortable with that, okay? It might be very much slower to train on the hardware, but once we've proved it out enough, then maybe we can create hardware to run it faster. Like in my lab, one of the most frustrating things is when we're sending papers out for review, the amount of times we have to remind the reviewer, no, it doesn't need to be state of the art, it can just be interesting. And I would like to see more of the AI industry accepting that fact and just trying different things and see what happens instead of just pushing the number up and making incremental changes.
So I do want to push back on this in a ring fight. So while Llion is perfectly right about the large matrix multiplication, he conveniently omits the softmax. The first generation of TPUs was made for serving RNNs, and it did not have the exponent in hardware. So the first time transformers were served, they had to offload the activations of the attention to the CPU, softmax there, and put them back. They were slow as hell. The point I want to make is they had to clear this hurdle. I gave a talk at Cerebras when they were founded, not long after, about the new transformer architecture. They were building hardware for something totally different. It didn't fit there at all. It had to prove itself to be good enough for the hardware company to change course, and now, 8 years later, they can serve it very fast. Whatever the post-transformer brings will need to clear a bar that's not just being 2x better. It will need to be 10x better. It probably will if it's a true... the existence of this bar is actually a blessing, not a curse, because otherwise you may get bogged down in improvements that are good, but just small tweaks. When you know you need to clear a 10x bar, you kind of free yourself to think big, and then the hardware we got, right? Yes, it's maybe not suited to your model, but I just have a laptop that's as fast as the 8 GPU box on which we developed the transformer. And actually, if you run RNN, it's a little bit faster because it's a single thing. The memory access is faster. So yes, you are 50x slower than the transformer, and no one should apply that bar. You should, if you show me a model that's just constant 50x slower, but on a better slope, you win. I have to give up. The hardware will follow when you show that, because people will, I think people understand that. A constant 50x factor, this will be overridden. Also, this year, and that is very new and very exciting to me, the agents can actually write CUDA, which is very new. I never learned to write CUDA, I must admit. I can write some Triton. So a lot of things that are just painfully slow on the GPU, you can overcome with the good kernel, which you don't need to write anymore. You just write the slow version and tell the agents, write it until the test passes that it gives you the same numbers, and that they're good at, right? They won't cheat you. So I think this narrows the hardware thing, and given the fact that for the price you can get now like much better hardware, I do think a lot of research is actually doable. I don't think it's a fair excuse anymore to say, well, you cannot beat the transformer at the same compute. No, that's fair, right? But you can find a model and show a curve that bends the right way. And that, I mean, please.
Yeah, I totally agree, but my feeling is I don't think enough AI researchers feel like that they can take this leap and show.
I will join you on this ring to tell them.
Okay, don't be scared of 50x slower. Don't be scared of not being as accurate as a transformer.
Well, hopefully we've converted a couple people today then. Should we do another question?
Yeah. Thank you very much. It's amazing arguments and opinions. And I remember at a certain point we talked about what intelligence is. I agree that intelligence is a process, but I feel there are something else for a different perspective. So I think intelligence is ability to relearning or de-learning or reframe the neural networks. Because we always associate intelligence with learning. For human, what is learning? Is we are changing our neural network connections. And I feel this way because I learned that, essentially we are inventing, no matter it's transformer architecture or other architecture, we are inventing neural networks. And neural network is essentially the same as it's silicon-based or carbon-based. In this room, we have many very successful neural networks in everyone's brains. And guess what? All of our neural networks not frozen, it's keep updating ourselves every minute, every second. And this is not only true for human, this is true for every organism in nature. So even an insect or even a small is keep updating their neural networks. But I think transformer, you train and then you froze it, and then you steering to everyone. You have to share the cost of the infrastructure, but even you don't share, you cannot let it learn while it's inferencing. So, what's your opinion?
Adrian, sorry.
If I can provide one maybe hint of the way I look at it, I'm not saying it's a good way to look at it, I'm just saying I look at it, but if you want to mimic the way people learn, you should look at the way in-context learning works in the transformer. You should not look at the backpropagation stuff, you should look at in-context learning, meaning you face a transformer with a new problem, a new riddle, you provide in-context 5 examples, and you look how it reacts. This is not a perfect analogy, but it's pretty good to be able to actually get mathematical connections around the two. So the way I would think about it is that, in an ideal world, intelligence would be like in-context learning extended to time tends to infinity, meaning having transformers that work as they work in context, but like on an infinite session in which they forget nothing and they actually pick up new skills along the way, rather than redoing what labs are doing in pre-training and so on and so on. So.
Yeah, I take your point. And I think it's a point for our side, because I agree that we have standard neural networks that have been around forever, and they were designed to have static weights, right? That's what they were designed to do from the beginning. And now 2026 is supposed to be the continual learning year, and we're supposed to be solving that apparently. Is that news to you? But it feels like a hack. We've taken something that's fundamentally built to have static weights, and we're like, oh no, now how can we add something on top of it so that we have dynamic weights? And I think I would much rather see someone develop something that was designed to have dynamic weights from the ground up. And that would be post-transformer-esque.
Just go ahead.
I'm not convinced this is a point for your side. Right, because transformers activations in the forward pass, it turns out after you pre-train it for a bit, do something remarkably similar to gradient descent on the backward pass in many ways. I think that's what Adrian was alluding to. So I would actually, as an engineer, prefer if this was explicit as training of the static weights. And I had this preference, and then someone told me that, but the brain actually has like fast and slow neurons too. So maybe I shouldn't have this preference. I don't know. What I would definitely though want is that any benchmark you do, like if it's a benchmark of Perplexity, it should be run on a really long context, and not on like random like LM1B, the old data set which was sentence level. I had this argument recently with someone about translation. He says, oh, the model translates so bad, and they feed them like half sentences to translate. Well, yes, you need to, like, if you're testing things, give them context, but 1 million tokens is a lot of tokens. So, it's like Harry Potter book is like 5,000 words all in total, I think, 500,000, right? So you can, that's already a lot. Like when it was 100 words, that was not enough. But when this context is so long, it's up to you whether you do gradient updates there or whether just activation updates. I will, I won't say which is the right, but yeah, the benchmark is there.
One more thing to add on is what if actually even the current architectural transformer
that's already be able to solve 99.999% of the problems that's already out there. Pretty efficient. It can be not necessarily significantly change the architecture, but just make certain optimizations from the system and platform. That problem will be solved. There is not necessarily always there is only one way of solving a problem, right? So that's why I think that people, even the transformer is still evolving, it can solve the most of the problems and can also be optimized for majority of the use cases. The transformer will stay.
I agree. The transformer is not going anywhere. It's too successful and too useful, right? So even in a post-transformer world, people will be using transformers, absolutely. Yeah. But on your point on like different models solving different things, that's a possible future, but sort of goes against the idea of an artificial general intelligence, right? We are looking for something that's able to.
That's another philosophical.
Right, that's true. But I did want to say, Lucas, your last point, touché. I take that argument, and I think something that is actually underappreciated about the transformer is that the attention weights are dynamic weights. They're not fixed, right? So yes, maybe the transformer is doing something akin to continual learning.
I want to add one thing from myself. The thing that actually pains me is that you need to say maybe. So we have amazing amounts of benchmarks, but I don't think there is a single benchmark that would be like, this is a context of, I think you'd fit it in 100,000 tokens. It defines some problem, gives you a few examples, and then it's almost like few-shot learning, but in something a little bit more complicated, where you could see in the Perplexity whether the in-context learning algorithm is actually doing a lot of work or just, because we have no real benchmark to measure how good is your in-context learning. We say, oh, well, we know it happens, but you know, it's like, poof, does it happen good, bad? I mean, you could measure it by perplexity of answers later, but our long context benchmarks are like needle in a haystack. I mean, this is not, you don't need to do learning, this is like retrieval, right? I think this is where, if anything, this is lacking, because that's where you could show with much less compute that a post-transformer model dominates. And like the state of benchmarks is I agree, is not where it should be, but that should be correctable.
And I think it's underappreciated how powerful in-context learning is at the transformer, making it very difficult to beat. For example, there's an amazing example of if you feed in tabular data, just like in text form, as doing time series prediction, it does actually a surprisingly good job of predicting the time series, despite the fact that it's text, not like floating points. So the in-context learning that the transformer is learning from this pre-training must be doing something much more interesting than we even realize.
Just wanted to add, this is definitely a point, and I'm on your side. There's one caveat to this. Of course, we can be asking if it's like 1 million tokens or 1 billion tokens or many billions of tokens where you need to get to when you get to kind of the ultimate answers of AGI. But the question is, where does this context come from? And there's a very easy distinction when looking at benchmarks, something to look out for. If we're looking at benchmarks where the context comes from like data that's just put into the transformer, that's one thing. And then there's a case when the context comes from the life path of the transformer, where it learned with experience, when it had its thoughts, where it's internalized its chain of thought. And that's the second case. That's the case that we do as humans, right? We don't have the context of the things like the encyclopedia that we read from, or the library we read from end to end, but it's the things that we did, the actions that we took, the reactions to those actions. And as soon as we get to a place where across a time horizon of millions of tokens, there's an architecture which is able to reason, update its thoughts, build like, working hypotheses, lemmas, prove things, check things, revise its opinions, and actually use that context effectively in that way, that is going to be an ultimate answer.
Fantastic. Matthias, anything to add to this?
Yeah, again, like I think it connects a bit to the point that I mentioned before. Like if you optimize the system around the transformer and the KV cache becomes so small, but you have an RNN that's like a bigger state, like I think they merge. Like I think it will not be staying like these two extremes, but in the future we'll see definitely evolution in both ideas.
Fantastic. Thank you so much, gentlemen, for this historical fight between Transformers, Łukasz, and the post-Transformers, brought to you by Pathway. So now we're going to decide who will leave tonight as the champion. Yay.
Make some noise.
Yeah. So, and since we love scientific precision... Sorry?
Can I ask one more question?
Who is asking a question? I think... oh, that's fine? Okay.
We've been talking a lot about context learning as the parallel to like human learning and continuous. I wonder when you would think about fine-tuning, like, because fine-tuning is maybe not as efficient as in context learning, but it's much more efficient than pre-training. So how that compares. And then also, there was earlier comments about reasoning in latent space, and I wonder if there's some fear around allowing models to reason in latent space rather than in text, sort of like leading to some type of existential scenario.
So I'm afraid
I can take the latent space thing. So I'm afraid that the fact that chains of thought are in text and currently fairly faithful to what the model does is a little over-relied on. Because you have these tokens, and the tokens are like whatever, few bytes each. And then you have the activations above them, and it's like dozens and dozens of layers of thousands of floating points, and we have absolutely no clue what's happening in them. So they are, like, when people say latent space, I understand. They want like a Gaussian vectors, and that's also fine, but there is a lot of latent space above these tokens. And just by pre-training, they're currently faithful, but one day you may see the same words said there, and the thoughts will be totally different, and I'm not sure you're gonna know. So I think we should not be complacent. Luckily, there's some work on keeping them faithful, but there is a lot of latents in the activations of the transformer already.
So this might be wishful thinking, but a post-transformer world might be us moving closer to something of how the brain actually works. And it might turn out that it's more interpretable and safer.
Yeah, I think we're kind of over time already.
We're going to wrap it up.
Yeah.
We're the final scoring. These guys are going to be hanging out.
Exactly.
We can talk to them later. We're going to get some food out here.
Precisely.
But right now, we've got to figure out who wins.
Exactly, and since we love scientific precision, your job will be to make crazy noise for the side you're rooting for. And whichever side is the loudest, gets the title, and then pretty much we have 4 trophies anyway. Okay, so.
All right, let's get the noisometer on the screen. We ready?
You have the devices, you know how to make noise? You know how to make noise? Let's have kind of just a round of noise first. Make noise? Yeah! Good. Alright, that was, we're not measuring yet. That was just practice! That was practice! Okay, stop. Can we measure again?
That was a great practice round.
That was a great practice. You do make a lot of noise, fantastic. Okay, now you're gonna. All right.
Let's give it up for Team Transformers!
All right.
And now, let's give it up for Team Post Transformers. Make some noise!
But you're getting close.
Very close. Wait a sec, Łukasz. You're getting the first trophy as the ruling champion. It's our job to prove you wrong. There you go, the rest of the trophy. guys, you are amazing. You're provoking and noise and everything. Make some noise for the speakers. Yeah. And now we can take a photo. Awesome. Yeah.